Yes, chapter number 6, momentum and Korean. Yes, momentum or linear momentum, we call it. Chapter number 4 is combined with chapter 6. As I told you in the original message that we will be doing a tutorial combined for both chapters 4 and 6. So we have one tutorial for 4 and 6 combined. That's why after chapter 4, I'm starting chapter 6 today. Linear momentum are simply momentum. We use letter P for momentum, and of course, it is a vector. Could you please turn off your, mute your mic, please? Could you please mute your mic? A little noise I'm hearing. Thank you. So letter P we use for momentum, or the linear momentum we call it. The linear momentum, of an object of mass m moving with velocity v. So the mass of the object is m moving with the velocity v is defined as the product of the mass and the velocity. You see, this is the mass, which is scalar, and velocity is a vector. So momentum is also a vector quantity. For example, if a person having, for example, 70 kg mass is moving with velocity 2 meter per second along the positive x direction, so its momentum, his momentum will be equal to the mass 70 multiplied by the 2 meter per second. You would get 140. You see, what is the unit for the mass? Kg. And what is the unit for velocity? So kg meter per second is its unit. Right. Momentum is a vector quantity, as I told you, that we multiply scalar magnitude of the mass, with the velocity, which is a vector. So momentum is also a vector. So momentum is a vector quantity, and direction of momentum is the same as the velocity. You see, this is the direction of the velocity, so momentum direction is the same. So velocity direction and momentum direction are the same. In this case, it is along positive x-axis. Now, momentum and Newton's second law of motion. You see, we have done this Newton's second law of motion in chapter number 4. This is acceleration, right? And acceleration is equal to change in velocity over time interval. The mass of the object cannot change. Velocity can change. So that's why we have delta V, change in velocity. Now, since the mass cannot change, so it doesn't make any difference if I keep this inside. So it's okay, no problem. Now, you see, the sum of the force is equal to, you see, delta M multiplied by V. What is M multiplied by V? What is M multiplied by V? It is the, I just finished this one. M multiplied by V is what? Momentum. Okay? P. Right? So, all right. Now, this is M multiplied by velocity equal to what? You see here? Can you hear me?
Yes, teacher, yes.
Good. So this is P. So can I write, instead of M multiplied by V, I write P over time. You see, this is what we started in chapter number 4, that net force, or the sum of the forces, is equal to the mass M multiplied by the acceleration. This is one form of Newton's second law. This is another shape, another form of Newton's second law of motion. Sum of the forces, or the net force, is equal to change in momentum over time interval. All right? This is what I have done it here already. The same thing I have done here, right? Okay. Right? So sometimes in this chapter, because we are studying momentum, that's why we are relating, the net force with the change in momentum over time interval. Okay, so that's why I give the heading Newton's momentum and Newton's second law of motion. Any question?
Yes, teacher.
Yes, please.
P, that's mean momentum or what?
Yes, momentum. Okay.
Okay.
P is momentum. P is momentum. This momentum P. Okay. This is momentum P. Right. Now, this is what I have written here, that it gives you an alternative form. Okay. This gives you another form. This is what I told you, that we have two forms of Newton's second law of motion. First, we did in chapter number 4 that it is equal to, the net force is equal to what? Mass M multiplied by the acceleration. So we have the second law, which is the alternative of the second form of the Newton's second law of motion, that we have net force is equal to delta P, change in momentum over time interval. Right? Okay. So this is what I did here. Same thing, delta M V over delta T. So that was equal to delta P over delta T. The same thing I have written here, by the way. Yes, next, law of conservation of momentum. What do you mean by conservation? Conservation means it remains constant. Once you measure the momentum of an object or system of objects at any initial time, and then you calculate again the momentum of the object or momentum of the system of objects at some later time, t final, both must be equal. This is what we say, that law of conservation of momentum. Momentum remains the constant. Okay, when no force is acting on the system. You see, when net force is equal to 0, what does it mean? You see, we have done the last example, last equation, that the second form, another form of Newton's second law of motion was sum of the forces or the net force is equal to change in momentum over time interval. Now, if I say net force is 0, what does it mean? It means, yeah.
Teacher, I have problem in Blackboard. I try to log in 3 times.
Blackboard?
Yeah, I have problem.
What's the problem?
I can't log in the first week.
Today? Now you are with me, right?
Yes, teacher. Yes. Yeah, but now I hear. But
No problem. That's good. No
okay.
Problem. Okay. All right. Now, okay. If the net force is 0, if this is 0, what does it mean? It means all this delta P over delta T will be 0, sir. What does it mean again? It means delta T cannot be 0. Okay. This cannot be 0 because time is passing, right? Time cannot be 0. It means this is equal to 0, sir. Delta P is 0. What does it mean again? If you have difference between the two quantities, delta P or delta X is 0, what does it mean? It means initial and final are the same. So P momentum, F for final. Final momentum is equal to, because this means delta P mean final minus initial is equal to 0. If I take it to the other side, it will become positive. So that's why I'm writing it here, that final momentum is equal to initial. Final momentum is equal to initial momentum. Again, we did study this on the last page, that Newton's second law of motion, says net force is equal to delta P, change in momentum over time. If we say, if the net force is 0, sum of the force is 0, net force 0, what does it mean? This is net force is equal to this. So if this is 0, it means delta P over delta T will be 0. Again, what does it mean? It means delta T cannot be 0. It's the time is passing. So it means delta P is 0. Change in momentum. When you have change in momentum, when you have final and initial. So I write it, final momentum minus initial momentum is equal to 0. I take it to the other side, it will become positive, and I'm writing it here. Final momentum is equal to initial momentum, right? Now, if, for example, you have any object having m mass, v final, m v initial, if you have only one object, but if you have system of object, like in this case, you have two cars, one having m1 mass moving with velocity v1, and the second car is having mass m2 moving with velocity v2, both in the forward direction. Okay, so net force 0, this is what I'm saying. System of it, this is, we call it system of interest. Yes.
Can you repeat the last step?
Okay.
MV final.
Yes. What is this? This is final momentum. Momentum is equal to m multiplied by v. So this is final momentum. So final velocity. Similarly, this is P is mean momentum initial. Mean P is m multiplied by v. So since this is initial, so vi velocity initial. Okay. All right. This is for one object. But if you have, for example, a system of two objects, you have two cars. This car with m1 mass moving with velocity v1. Second car, you have the mass m2 moving with velocity v2. Okay, so if you calculate momentum of the first car p1 plus momentum of the second, so you will get p total momentum at initial time, okay, before collision, before starting, and after what happens, we have p1 prime, p1 dash plus p2 dash, momentum of first car plus momentum of the second. Okay, after I'm using this prime or the dash is equal to total. Okay, because now the velocity changes v1 dash after some time and v2 dash for this car. Before v1 and v2, now v1 dash and v2 dash, or you say v1 prime or v2 prime. Okay, so we use this idea when we say that momentum of a system remains constant. Constant means it is conserved, so we call it conservation of momentum. All right. Impulse. Right. You see, we discussed last page this equation many times, delta P over delta T. Right? If I take this delta T and then it will come with F. So F and the time multiplied. Okay. So I can write it F, okay, sum of the forces, net force F multiplied by delta T. On the right side, you'll be left with delta P, change in momentum. You see, this is the product of multiplication of two parameters. One is net force F, the second is time interval. Okay, so this multiplication of force and time interval, we call it I. Okay, this is I. Okay, here, this is I. So F multiplied by time interval, we call it impulse. Okay, الدفع. All right. So impulse, which is force multiplied by time, as you see here, is equal to change in momentum. The same thing I'm writing here. Force multiplied by time is equal to delta P, and force multiplied by delta T is impulse. So impulse is equal to F multiplied by T, or impulse is equal to change in momentum delta P. When you have change in momentum, when you have a final minus initial. Okay, final is this, initial is this. M mushtarak, common, so inside you'll be having this one. All these things are simple mathematics. Whatever you like, you can rearrange the equations. Any question, please?
Clear, Doctor, clear.
Good. Right. Now, so you might have seen this momentum change or the collision, you see, in at many places. Sometimes you have big accident, you might see big accident on the roads, and even in the industry. Okay, so you call it, what do you call it in Arabic? Tasadam, huh? Okay, right. So let's do the example on page 6.2. This is very small chapter. We have two examples. Please have a look, and then we will solve it in 1 minute. Please read it carefully. Yes, please. You see, this is a typical, they call it a crash test. Whenever the manufacturer of the car, they are manufacturing the cars, before bringing them in the market, they have a full fatigue test and crash test, so that they have dummy drivers within the car, not the actual drivers, by the way, and they give it a velocity on one side, and it touches the wall, it collides with the wall, and bounces back. Okay, so for example, take this side positive x-axis and this side negative x-axis. Okay, now a car of mass, so the mass of the car is given to you. Okay, so this is mass of the car, right? Collides with the wall and rebounds. Rebound means rebounces, goes back. After touching this surface, it goes back. And the initial and final velocities are given. For example, initial velocity, it is going to the negative side with 15 meter per second. That's why he has already given it minus, because it is traveling towards the negative direction. Okay, so VI is 15 meter per second. M is 1.50 kg, right? And final velocity, this is minus, right? Initial velocity minus 15 because along negative x-axis.
Yes, minus VI.
Final velocity is 2.60. It's positive because it is going to the positive x-axis. So this is the final velocity and this is initial velocity.
Teacher,
Now,
excuse me.
yes, please.
VF means after the collision, go back.
Aywa. You see the car is coming, this car is traveling toward the negative x-axis. When it touches, it collides with the wall. So this is it is traveling with the 15 meter per second along negative x-axis. So minus 15 meter per second initial velocity. Once it hits the wall, it goes back in the opposite direction. I mean to the positive x direction with 2.6 meter per second. Okay, if the collision lasts for 0.150 second, so time is yes, delta t is this is meter per second. So delta t is equal to 0.150 second. Okay, you see, whenever you are having some collision, you are transferring energy from one object to the other. Once you are kicking a football, you are transferring energy, right? Or you are transferring momentum, right? Actually, in chapter 4 we studied what happens when forces are acting on some object. In this chapter 6, what we are focusing, yes, of course, forces are acting on the objects, but the important thing is, what is the time of contact? For how long time when the force is applying on one object, how much time it spent? You get the point? So time is very important also. Okay, for example, if I say once you kick a football, you press football, your foot presses football because there is some air and easily, and think about this one. But if you kick a stone of the same size of the football, you will feel hurt, right? Because the time is very small and it is very solid object, the stone, not like the football that your foot takes time to go to push it, right? Right. So anyhow, so this is the example. So we have to find out first of all the impulse delivered. We just finished that the impulse is equal to force multiplied by time. Since we don't have force here, or we have the change in momentum, this is what we studied in the last topic here. You see, impulse is equal to force multiplied by the time, or delta p, change in momentum. So I am using impulse is equal to change in momentum, which is equal to this one further. So is equal to mvf minus mvi, which is equal to m how much? 1.3 vf 2.60 minus initial how much? Minus 15. So this will be minus will be plus. So finally you will get in kg meter per second 2.64 Yes, 2.64 into 10 raised to power 4 impulse. This is in kg meter per second. Any question, please?
تقريبا.
It's okay.
You have two rules.
Sorry?
Two rules. MV F
Yes.
minus MVI.
Yes. This is one rule. Because you see, you have in fact, I told you in the last page that you have first of all Newton's second law of motion, this one form, right? So we discussed that force net is equal to m delta v over delta t, and that was equal to change in momentum over time interval, this force. Now if I take this to the other side, you will get f multiplied by time interval, and on the one side you will be having delta p. This is called impulse. So you have impulse is equal to this rule, or impulse is equal to delta p. So I am using right now impulse is equal to delta p. Delta p means final momentum minus initial momentum, means for m multiplied by f, vf minus m multiplied by vi, because momentum is equal to m multiplied by v. So m is common, mushtarak. So vf minus vi is equal to impulse. This is what I am using in this example. This one, okay? You get the point?
But this page what rules? Page what?
Sorry?
Page what?
Page?
What's the page?
This page
168.
example is 170. 170.
Yeah, teacher.
Rule is on 168. That rule is on page 168, and this example is on 170.
What about delta t, teacher?
Sorry?
What about time? 0.150
It's given.
second. What about time? What did we do?
We will use it. No, we don't use it here, because sometimes you are given, you know, flour, sugar, you know, oil, all these things, and you are given also red chilies, and you are asked to make the cake. So you will not use chilies in making the cakes, huh?
So to confuse us, teacher, or
No, actually, sometimes like here, it will be used in the second part, B part. So this is the part.
but
Okay.
the rule, teacher, is F equal mass V delta V. Yes, here.
Okay.
F equal mass delta V over delta T.
This one.
We didn't put delta T, teacher.
Delta T, I'm
Verify.
making it here, F multiplied by T. I told you 2 times. I proved it again second time for you. What is A? Change in velocity over delta T, right?
Yes.
A, acceleration. So I take this M multiplied by V. M multiplied by V. it is equal to P, right?
Oh yeah.
MV is equal to P. So I'm using here MV P here. Okay.
Delta B is the same mass multiplied by V. Delta V.
No.
M V equal to B.
See,
Yeah.
P is equal to MV, but delta P is equal to M delta V. Mean M delta V, MVF minus VI. Okay.
Okay. So the last rule here, I equal to M mass multiplied by VF minus VI. We do, when we use it.
It depends what is given and what to find out. So once you write all the given information like this one, initial velocity given, final velocity given, the mass is given, time is given, so you will find which rule you need. So you need first of all calculate the impulse. Okay, so impulse, we know that it is equal to force multiplied by delta T. We don't have force here, so we will not use that rule. So we'll be using delta P.
So he is going to ask you what he wants.
Exactly. Sure.
Oh, okay. Thanks, teacher.
Welcome. Should I move to the second part, or you need time to note it?
Oh, thanks, teacher.
You want to take time?
I'm done.
Okay, guys. Second part of the question now. The size and direction of the average force. So you need to find out the force or average force here. Okay, mean size, mean magnitude, direction also, both. Which direction? Okay, so we have done this rule that force is equal to delta P over delta T. We did it, right? Here. Here. This one. You get it? We did it, sir. Yes? We did it. This rule.
Yes, yes.
Yes.
Right. So this is net force or the average force, delta P over. Now you have already done in the previous part that impulse or delta P is equal to this much. Okay, so this is impulse. You call it impulse or delta P, the same meaning, right? So delta P is this much. Okay, so delta P is how much? 2.64 divided by time. You get, what is the unit of force? Newton. 1.76. You see, this is positive, right? Okay, this is size of the size or the magnitude of the force, and since direction is positive, mean direction is along plus x-axis. Okay, right? So this is the size or the magnitude, and the direction is plus, because you see, you can see here it's going to the negative x-axis. After collision, it is going back towards positive x-axis. This is clear in the from the picture also, but from the numerical value also you can say that it's positive, so along the positive x direction. Yes, please. Let's go to the next last example of chapter 6, very small chapter, by the way. Take 2 minutes to read it, then we will solve it. Yes, please. Example 6.3 on page 174, the arcer. We will do only a part. Calculate the recoil velocity using conservation of momentum. An arcer stands at rest. So if I make like this one, I have 1 and 2. Okay, this is arcer and this is arrow. Okay, arcer means the man. Okay, he is the arcer or the man, and this is his bow. It's arrow. Right. let me call it, it's 1, so I call it M1. This is M2 at rest. So the person is at rest. So, you know, initial velocity for first object is 0 given, right, at rest. His total mass, including his bow and quiver of arrows, is 60. You see, total mass is 60. So it means M1 is 60 minus M2. M2, how much? Okay. If the archer fires an arrow, this is arrow, and M2 is 0.030 kg. So total is 60, you see. This is total, and this is 60 total. So 60 minus 0.030. So M1 becomes 59.97 kg. Okay, the man is at rest, the archer is at rest, so V1 I initial 0 and V2 I is equal to, the archer fires in the positive x direction. What is his subsequent velocity across the ice, right? So the final velocity for the arrow will be 0 when it hits some object, right? What is the subsequent velocity across the ice? Okay, so you have to find final velocity of first object, which is a person. So this one you need to find out, whereas it is written that if the archer fires an arrow horizontally 50 meters per second, this is the velocity for the arrow. So it is 50 meters per second. You have to find out initial velocity of the person. Okay, no, sorry, final velocity of the person. You see, once you fire, you might have experienced while in playing or firing a gun, for example. So once you fire a bullet in the forward direction, you feel a jerk in the opposite direction, backward. So he will be moving backward. Just keep in mind, please listen. Archer is firing along the positive x direction, right? Person will move a little in the backward direction along the negative x-axis. So keep in mind that once you get the answer, final velocity for the first object, which is the person, the archer, you must get negative velocity. You see, he's firing arrow on the right side, positive x-axis. He himself will feeling a little motion, a little jerk in the negative x direction. So you will be getting this minus, keep in mind from right now. You see, we are using the conservation of momentum, which says that final momentum is equal to initial momentum, right, of the system. Now you have a system of two objects, a person, archer, and the arrow, two, and we have all the data here. Okay, this is final. Okay, keep in please focus. You see, this is the final momentum for the person, for the archer, plus this is the final for the arrow must be equal to initial. Listen please carefully. Listen carefully. Initial, you see, when you have not fired yet, you are at rest. Your bullet or your, in this case, your arrow is at rest. So both are having 0 velocity. You see this one, you see, initial velocity of the person is 0. He's at rest, not fired yet. And the arrow is also at rest, not fired yet. So multiply by their masses, you will get 0 plus 0. Is it okay, please? So that I will move forward then. Are you okay up to here? Any problem? Ask me now, please.
Excuse me, teacher, again, please.
The last one, this one equation?
Yes, from PF equal.
You see, we have done here this one. Conservation of momentum. Final momentum is equal to initial momentum, sir. This rule I am using.
Yes.
So this rule I am using. Now you are not having one person, you are having 2 objects. We have a system. Okay. System you have now of 2 objects. Archer, which is the man, plus arrow. This is the system. So archer or the man, I am taking it as 1, and the arrow I am taking as number 2 objects in the system. So their masses given, total mass is given 60. So this is the mass of the arrow. So what will be the man of the archer or the person? 60 total minus this one, you will get this one. This is what we did. Now initial velocity of both 0. Once initial velocity this 0, so this 0 multiplied with the mass, which is the momentum initial for this man, will be 0. Similarly, initial velocity for the arrow is 0. Even 0 multiplied by this mass, again you will get 0. Sir?
Yeah, okay.
Good. Initial momentum for the man and for the arrow both 0. But the final momentum for the man, because man, the archer, I am taking 1. So M1 the mass, V1F, you have to find out V1F. Whereas V2F, final velocity for the arrow is given to you, which is 50 here, sir. Now, I need V1F, so I will keep this on the left side and I will take this to the other side. It will become negative, sir. Minus M2 V2F. And here you have M1 V1F. Okay. Now I'm taking this side, please. I need M1 V1F. I will take this M1 down here, other side, right side. So V1F will be equal to minus M2 V2F over M1. So how much? M2 0 point. M1, this is M1, 59.97 multiplied by V2F, 50. So 50, you would get, V1F minus, because I told you in the beginning that arrow is being fired on the right side, so person will feel a little jerk, a little motion on the opposite direction, minus x-axis. So I told you that you will get minus, so it's okay. Okay, 0.025 meter per second. This is your answer. Okay.
Yes, okay.
Good. So this is end of 6th chapter. I'm going to leave the session now so that this recording will be separate, and I will start tutorial chapters 4 and 6 together after 2 minutes. So give me 2 minutes, please, and don't leave. And